Hello and welcome back to Calculus, the series where we explore integrals. First, I'd like to thank all the nice people that support this channel by liking and subscribing. It helps massively for me to make more videos for you to enjoy. In this short video, I'd like to show you the two simple ways to solve a definite integral by substitution. However, before we get to that, first, please recall the fundamental theorem of calculus I talked about back in part 17. It basically states that if we have a function f that is continuous, where continuous means we can draw the function without lifting our pen, on an interval from a to b, in this case a is smaller than b, and we also have that the capital F is an antiderivative of the small f, then in this case, when we are solving an integral from a to b of the function f of x, then what we do is we take our antiderivative function and plug in the larger value and subtract by plugging in the lower value. In other words, we plug in the upper and lower bounds of the integral into the antiderivative function, and the answer that we should get is a real number. However, you might ask why we make a separate video for definite integrals by substitution. Solving it should be the same as before. And this would be partially correct, but not completely. Because when we make a substitution, we change our variable x into u. Hence, when the integral says dx, we also have to change it to du. That means the bounds on the integral, which originally belonged to the x variable, will not always be the same as the bounds for the variable u. So in order to understand this better, let's immediately take a look at an example. Let's say we're tasked with finding the value of the definite integral from 0 to the square root of 3 over 2 of the function 2x times square root of 4x squared plus 1. Well, the first step we would take would be to find the antiderivative of the function, meaning we do have to make a substitution. And the obvious substitution would be everything under the square root, in this case 4x squared plus 1. So now when you do du over dx, what you're going to get is just 8x. In other words, du is simply equal to 8x dx. So now, after the substitution, the revised integral we're going to get would be with 1/4 in front, integral of square root of u du. Now, what do we do with the bounds? There are two ways to deal with this. You can write the bounds as x equals to 0 and x equals to square root of 3 over 2, indicating that your bounds still belong to the variable x. And then, when you keep solving this, what you're going to get is the following. So now that you got the antiderivative function and you have your bounds, that means you can take the substitution, put it back instead of u, and then keep evaluating the integral. And I can tell you immediately that the answer you're going to get at the end should be 7 over 6. This method here is the obvious one. You do the substitution, you still keep the bounds for the x variable, you find the antiderivative function, make it back into the x function with the variable x, and then plug in the original bounds. However, there is another way I personally find more comfortable. I will write it here as the alternative solution. Again, the substitution remains the same, however, we're going to do something about the bounds. The good thing is, if you have the substitution and the bounds for x, you can actually calculate the bounds for u. What you can do is take the x bound. For example, we take the upper bound for x, which is square root of 3 over 2, and we plug it in into the substitution. In this case, that would be 4 times the square root of 3 over 2 squared and plus 1. The answer you're going to get here is simply 4. And then you do the same with the lower bound. You take x equal to 0 and you plug it in into your substitution. In our case, that would be 4 times 0 squared plus 1, meaning the lower bound is going to be 1. So now, these two numbers, 4 and 1, would be the upper and lower bounds for the variable u. That means the revised integral after the substitution would be 1/4 integral from 1 to 4 of the square root of u du. Now you do the same. You find the antiderivative function, only now it's just going to be from 1 to 4. And the good thing about this is that you won't have to plug in your u substitution back into the antiderivative function. Now that you have the bounds for the variable u, you can just immediately do 1/4 times 2 times 4 raised to the power of 3 over 2 over 3. You immediately plug in the upper bound and you subtract by plugging in the lower bound. So in this case, 2 times 1 raised to the power of 3 over 2 divided by 3. And magically, the answer you're going to get is still 7 over 6. So, in conclusion, both of these methods are correct. It's all about personal preference. I personally prefer the second method, changing the bounds for u. However, some people might find it confusing and stick with the original one, where we keep the x bounds and simply plug the substitution back into the function. They're both good. Below, I will leave a definite integral for you to solve by substitution, and I will also attach the work solution. If you want to access it, just go to the video description where I publish the PDF version of all lessons for free. If you want to find the PDF version of previous lessons, there is a separate link to the entire calculus folder, which is updated every time I make a new video in this series. So that's it for now. Next time, we will take a look at a more complex integration method. So I really hope to see you there and have a nice day. Bye.